Howdy. The point of this video is to cover some of the important concepts from quantum mechanics and to understand how this affects electronic structure of atoms and of matter as a whole. So why do we care about quantum mechanics? Really this is a description of things at a very, very small scale, and maybe you might think that it's not particularly applicable to large macroscopic physical objects and their properties. As I mentioned before, quantum mechanics is a description of the electronic structure of atoms and of matter. And so that means if we want to talk about electron densities, if we want to talk about bonding, if we want to talk about any physical properties that are related to electronic structure, so definitely electrical properties, optical properties, thermal properties, all of these are affected by the structure of the electrons in a system. And so that means to really understand this structure, we need to know something about quantum mechanics. So just a couple examples. Here's one study where we were looking at introducing foreign particles and bits of catalysts into a system to understand how that changed the electronic density in the material, which could potentially affect how it reacts. So these are catalyst particles. One other example is understanding the electronic band structure of materials. So this is an example of graphene, and we're plotting energy in momentum space here. And really, the band gap and the curvature of these electronic bands as they get close to each other affect how electrons move through the material. We call this electronic transport. In both of these cases, to get a good physical understanding of the system, we need to know something about quantum mechanics. Okay. So what is quantum mechanics all about? It became clear at some point that electrons are not very well described as just point particles. So this fellow Schrodinger came along and asked the question, okay, if an electron has wave-like properties, there must be some sort of equation that governs the property of those waves. And so Schrodinger's big contribution was the introduction of the Schrodinger equation. So this comes in a couple different variants. There's time-independent, time-dependent, non-relativistic, relativistic forms. We're going to focus just on the time-independent, non-relativistic form for the moment, and try and understand what it means. And really, all of this equation says is that if I'm going to describe an electron by a wave, some sort of wave function, it has to satisfy a certain condition. And that is when I operate on that wave function using what we call an operator, this is called the Hamiltonian operator, I'm going to get the same wave function back times a scalar, which is the energy. So this Hamiltonian operator can just be broken down into two different parts. There's something that describes the kinetic energy, and there's a part that describes the potential energy. So this might look a little weird, might look a little bit like complicated math, what's going on. But you've experienced things like this before. When we talk about classical physics and you want to talk about the kinetic energy of a particle, we say kinetic energy equals 1/2 mv squared. So the kinetic energy in this case is related to some other property, in this case the velocity of the particle. So all this is doing a very similar thing. It's just saying if we start off with this wave function that describes the electron, we operate on it by a mathematical operator, and what we get back is the wave function times the overall energy product of the material. So you see here I have left this ambiguous. This is just some potential energy function that is a function of the distance from the nucleus. So depending on the system, we could consider introducing different sorts of potential energy functions. So one of the classical problems that you'll see in quantum mechanics is called the particle in a box. And so we describe some potential energy function that it has zero potential energy over some distance range, and outside that box, the potential energy is infinite. So that's one particular case. If we're talking about an atom, then this potential energy is going to be given by the interaction between the positively charged nucleus and the negatively charged electron, right? So in this case, if I want to describe the potential energy for a hydrogen-like atom, I can use the Coulombic potential, which, if you remember, is charge 1 times charge 2 over 4 pi epsilon naught times the distance between the two charges. And in the hydrogen atom, the charge on the nucleus is positive E, the charge on the electron is negative E, and so we get negative E squared over 4 pi epsilon naught R. So, so this is a specific case of the time-independent Schrodinger equation for a hydrogen atom. Now again, remember, this is just describing some wave function, which is describing the electron. So in order for a wave function to describe the electron in the hydrogen atom, it must satisfy this condition. So this looks a bit complicated, but it's possible to solve it. And this is what Schrodinger did. He went in, he broke down this problem. He broke it into radial components and spherical components and found a solution to the very simple case of a hydrogen atom, which has one positively charged nucleus and one negatively charged wave function around it. So again, this might look a little complicated. We're not going to derive it here. That's what you would do in a introductory quantum mechanics class, something like physical chemistry. But we get a potential solution. L stands for the Laguerre functions. Y here are the spherical harmonics. So this is potentially a little confusing listening, but what I want you to realize is that this is giving us not a single wave function. This is giving us the conditions that a wave function must satisfy in order to be a solution to the problem, the description of the hydrogen atom as we set it up. So for a wave function to satisfy this condition, we see a couple N's and L's and M's in here. So these are all integers. And the only solutions to this particular wave function are given when N, L, and M are specific integers. Okay, so let's review this one quick time. The Schrodinger equation just describes the conditions that have to be satisfied for this electronic wave function to exist in a system. So we can define our system. For the hydrogen atom, we put in Coulombic potential between a positively charged nucleus and a negatively charged electron orbiting around it. And we found a set of solutions that describe potential wave functions that electrons can occupy for this case, for the hydrogen atom. Okay, so, but what do these mean, right? First, let's look at these integers and see what values they can take. There's basically a certain set of rules that comes out of this, this solution to the hydrogen atom. N, we call this the principal quantum number, can take values of 1, 2, 3, et cetera, et cetera, et cetera. So it can take positive integer values. For each number n, L can take some integral value from 0 all the way up to n minus 1. So in the case of n equals 1, L, and we call this the angular momentum quantum number, or sometimes the azimuthal quantum number, can take values from 0 up to n minus 1. So for n equals 1, L is restricted to 0. For n equals 2, L can be 1 or 0, and so on. M sub L describes the magnetic, it's the magnetic quantum number, and this ultimately is going to describe an orientation of our orbitals. So M sub L is allowed to take values from negative L all the way up to positive L. Again, still just integral values. So for example, in this case, n equals 2, for L equals 1, M sub L could be -1, 0, or 1. Or for L equals 0, M sub L can only be 0. Finally, M sub S, and we call this the spin quantum number, can take values of +1/2 or -1/2. Okay, what do these numbers mean? What we typically have learned in our introductory chemistry, and in fact, chemistry as far back as high school, maybe even before that, is we talk about orbitals, right? We talk about 1s, 2s, 2p, these sort of things. So the quantum numbers, again, remember these are numbers that give a potential solution to the wave function. What the physical interpretation of the wave function is that the square of the wave function is proportional to the probability density. So the probability of finding some electronic density in a given region of volume. So that means that we can look at the square of the wave function, and it'll give us some idea of the shape of the electronic orbital. So n, remember this is the principal quantum number, we usually refer to this as the shell. So if n is 1, this is the first shell. If n is 2, this is the second shell, third shell, so on and so forth. L, the azimuthal quantum number, or angular momentum quantum number, gives us some idea of the shape of that orbital in the distribution of that orbital probability density in 3 dimensions. So this is the shape of orbitals. So for L equals 0, it gives a spherically symmetric shape. So these are the s orbitals. For L equals 1, we have one node, so one plane where there's 0 probability of finding electron density on that plane. So these are the p orbitals. For L equals 2, we have 2 nodes. For L equals 3, we have 3 nodes. This one is a little bit more difficult to draw. So this describes kind of the spherical distribution of the probability density of that wave function. So again, L is 0, we refer to as s orbitals. L is 1, we refer to as p orbitals. L is 2, these are the d orbitals. And for L is 3, this gives us the f orbitals. Finally, M sub L, this is the magnetic quantum number. This talks about the orientation of those orbitals. So for an s orbital, there's only one possible orientation because it's spherically symmetric. For a p orbital, we could have that node along the x equals 0 plane, along the z equals 0 plane, or along the y equals 0 plane. So the orbitals oriented along the x-axis, along the z-axis, or along the y-axis. For the d orbitals, it gets a little bit more complicated, and even more complicated still for the f orbitals. But all of these describe the orientation of those orbitals in three-dimensional space. So that is the magnetic quantum number. Okay, here's another visualization of what these orbitals look like. So let's look at just one set first of all. So remember, L is the angular momentum quantum number. L equals 0 are the s orbitals. So these are all spherically symmetric. For n equals 1, these would be our 1s orbitals. And so there are no nodes in the n equals 1 case. In the n equals 2 case, 2s, there's one sphere, and it's a little difficult to draw in this case, but it's right around here, that there's no probability of finding an electron at that particular radial distance from the nucleus. For the n equals 3, that's 3s case, there's 2 nodes. For the n equals 4, 4s case, there's 3 nodes. And I can show you 2 of them. The third one is too close to the center to visualize really easily. And so on. So these are the s orbitals in increasing shells. So one thing that we immediately notice is as I go to higher and higher principal quantum numbers, the radial distribution gets further and further out. And so we could talk about that in terms of the radius of the atom. The distance at which we're likely to find an electron is getting larger and larger at increasing shells. Okay, let's look at the second set. So L equals 1, again, this is the angular momentum quantum number. The first case, I have one planar node, so this is the 2p. In this case, I have a planar node and also a radial node. So these are the 3p. And it proceeds downwards. So in all of these cases, I have one planar node, but an increasing number of radial nodes. Just like the S case. At higher and higher principal quantum numbers, we have more and more radial nodes. For L equals 2, these are our d orbitals. So we have 3d, 4d, so on. So a couple of things that we see immediately. There is no such thing as a 1p orbital. And that's because, remember, for n equals 1, the angular momentum quantum number can only take values from, it can only take values from 0 up to n minus 1. And so for n equals 1, this is 0, so the only acceptable value of L is 0. So we have a 1s, but no 1p, no 1d. So we only introduce p orbitals in the second shell, d orbitals in the third shell, f orbitals in the fourth shell, and so on. So how does this relate back to the periodic table, the organization of electrons and atoms that you're used to seeing? Okay, let's think about this again. So for n equals 1, I only have an s orbital. Remember, m sub s, the spin quantum number, can take positive 1/2 or negative 1/2. So that means I can put 2 electrons in each orbital. So the 1s atoms are hydrogen and helium. So hydrogen has 1 electron in the 1s, helium has 2 electrons in the 1s orbital. Let's go to the next shell. So for n equals 2, I could have 2s orbital, and so that gets filled by lithium and beryllium. But now I can also have the 2p orbitals. Now 2p orbitals, there are 3 different orbitals. Each are given by a different magnetic quantum number. And each of those orbitals can have positive 1/2 or negative 1/2 values for the spin. And so 3 orbitals times 2 electrons means that there's 6 different there's 6 electrons total that can go in. And so filling those up sequentially, we fill this second row block of atoms over here. And we would proceed on, right? So we have 3 s electrons, 3 p electrons. The third shell can have d orbitals, but these don't get filled until a little bit later. And we'll talk about this in the video on electronic filling rules. Okay, so in review, quantum mechanics is necessary for us to describe electronic densities, for us to describe bonding between 2 different atoms, and really for us to describe any sort of electronic, optical, magnetic properties. These are all functions of the electronic electronic distribution in a material. What are the quantum numbers? The quantum numbers are simply these integers that give different potential solutions to the Schrodinger wave equation for some atom. So we can derive the solution for the hydrogen atom, and I showed that to you. We didn't derive it, we just showed it. We can't actually solve the Schrodinger equation for anything more complicated than the hydrogen atom. So if we have a system that has even 2 electrons, that's too complicated to solve. So we have to start introducing approximations and different ways to get close to a solution. But this is what we're doing computationally these days in what's called density functional theory and quantum mechanic modeling. These quantum numbers, the physical significance is that they're describing both the energy levels of a potential orbital and its distribution, the electronic distribution around an atom. So we can think about these as describing the traditional orbitals that you learn about in chemistry. Finally, these 4 quantum numbers, n, l, m sub l, and m sub s, they all have slightly different interpretation. Right? The shell tells you something about the overall energy and how far out this distribution is. The angular momentum or azimuthal quantum number talks about the spherical distribution of this electronic density. So really, it's telling us about what kind of orbital. M sub L gives us orientation. So we could have the p orbitals oriented along the z, along the x, or along the y axis. And finally, M sub S is the spin quantum number. And this can always be either spin up or spin down, but this is what gives us 2 electrons in each potential orbital.